Hello there, and welcome to this live session of the Chemistry Clinic brought to you by Boost Revision. I'm Dr. Owusu. In today's session, we're going to be looking at some qualitative chemistry, and in particular, we're going to be looking at test tube reactions to identify organic functional groups. And as usual, I will be towards the end of the lesson looking at some actual exam questions on the topic we've just looked at. If during the course of the session you've got any questions for me, please do use the chat function and I will be stopping intermittently to check on these questions and answer them for you. Before we start, I'm going to share my tablet with you and then we'll be ready to go. So just give me a few seconds while I do that. Fantastic. So you should see on your screens at the minute the title page, which is Practical Chemistry and Tests for Organic Functional Groups. Of course, this session is relevant to both years of the A-level course. So we'll start with a summary of the different functional groups that you're required to know and be able to test for at A-level. So on your screens now, you should have a table looking at the key functional groups in question. If I zoom in a bit more. Alkenes, of course, so perhaps the first example of a functional group that you'd have come across at GCSE and one that you were taught to test for is the alkene functional group. So we're going to be looking at alkenes. We're also going to be looking at the test for a carbonyl functionality. Now, while it says carbonyl, it only strictly refers to aldehydes and ketones. So 2,4-dinitrophenylhydrazine, which is shortened to 2,4-DNP, is the reagent that you would be using in that case. And it only really tests for the presence of the aldehyde or ketone carbonyl group. There are other functional groups that contain carbonyl groups, such as carboxylic acids or esters or amides, but none of these react with 2,4-DNP for reasons that we shan't go into. Okay, and then more specifically, we'll be looking at a test that allows you to distinguish between aldehydes and ketones. And in this test, so there are a couple of tests I will be reviewing with you. Tollens reagent is the most common one encountered at A-level, but there are a couple of others, and we'll look at one of these, which is Phenolic reagent. Another test you're required to carry out is a test for the presence of the carboxylic acid group. And in this test, you are typically going to be reacting your unknown solution with sodium carbonate or sodium hydrogen carbonate. And if there is a carboxylic acid present, then the two react to produce a gas, which is, of course, carbon dioxide. And then we'll also look at the tests for alcohols, but in particular, primary and secondary alcohols, and the fact that both of these can be oxidized by a reagent such as acidified dichromate allows us to have a simple, handy test tube reaction that can identify the primary or secondary alcohol. And we will spend a little bit of time considering why tertiary alcohols can't be oxidized in the same way and so can't be positively identified using acidified dichromate. We'll also look at the halogenoalkane functionality, so where the halogen is chlorine, bromine, or iodine. We'll look at how you can show that these halogen atoms and the halides that are formed as a result of hydrolysis are present using silver nitrate. And we'll look at how to distinguish between the different halide products formed. And then finally, phenols are another functional group that you're required to look at A-level. The phenolic group is acidic, but only very weakly acidic, weaker than the carboxylic acids. And so you can react phenols with metals or say sodium hydroxide, and they will behave in much the same way as other acids in that you would form the sodium salt in both cases. But in the case of phenols reacting with sodium carbonate, there is no reaction, unlike in the case of carboxylic acid. So we'll be looking at that particular method for identifying the phenolic group and for telling it apart from, say, weak acids such as carboxylic acids. Okay, so that's our summary table. But let's look at each of these functional groups and look at the detail of each of the tests you should be able to carry out. remember that you would be required to give an accurate description of how to carry out the test, as well as what observations are relevant to allow you to identify the presence of a particular functional group. So experimental detail is very important. Okay, so to start with, we're going to look at the alkenes, and this should be familiar to all of you. All GCSE syllabuses look at alkenes and how to test for the presence of alkenes. In more general terms, the test for the alkene carbon-carbon double bond is really a test for unsaturated, or unsaturation, I should say. So this is a test for unsaturation. Okay, so it's more generally a test for the presence of carbon-carbon double bonds. Now, if you've got your sample, your unknown sample, and you add a few drops of it, you only need 2 or 3 drops of your sample to about 1 centimeters cubed of bromine water. Bromine water is simply bromine dissolved in water. It's a dilute solution of bromine in water. And if you add a few drops of your sample and the bromine water changes color from orange to colorless, then you know that you do have a double bond present. So why does this color change happen? So if we consider bromine, now bromine is of course molecular, it is diatomic, and it's got 2 bromine atoms. And in this instance, the bromine is reacting with an alkene there. Now, you will have already seen in previous sessions on organic reactions of alkenes and mechanisms involved that you've got an addition reaction happening in this test, and your bromine is going to, as it approaches the double bond, there is going to be an induced dipole in that bromine molecule, so that your pi electrons in the double bond will attack the bromine molecule. And one end of the bromine molecule is, of course, Br delta plus, and the other end would have a delta minus. So the pi electrons in your double bond will attack the Br with the delta plus on it. That adds a bromine atom to one of the carbons. So you form a carbon-bromine bond. You have an intermediate formed, which is of course a carbocation, and that carbocation will be attacked by the bromide ion that you formed after the first stage of a mechanism. Okay, so I will ask you to go off and review the electrophilic addition mechanism and generally the reactions of alkenes if you've forgotten or if this isn't familiar to you. So the result of this addition reaction, so again, this is an addition reaction. And this is an electrophilic addition mechanism. Okay, so the result of this is that your bromine dissolved in water, which is usually orange, depending on how concentrated it is. It might be sort of more straw-colored, a bit yellow, or orange. Once that's been used up, there's no longer any bromine dissolved in your water. That orange color disappears because you've now broken up the bromine molecule into so that you can add bromine atoms across the double bond. Okay, so as a result, you go from an orange solution to a colorless solution. Okay, so that is the test for alkenes, and one that you should be familiar with from GCSE, but also in the first year of A-level. Okay, so let's move on to the next functional group then, which is the test for the carbonyl group in aldehydes and ketones. Okay, so the reagent we're going to use, or the reagent that would be used if you were allowed to carry this out, would be 2,4-dinitrophenylhydrazine. Now, 2,4-dinitrophenylhydrazine, or 2,4-DNP, is very sensitive to shock, and it is an explosive, so I couldn't get that word out. And so, if used at all, it would be provided as an already made solution. It's also potentially carcinogenic, so unlikely to be sort of seen in the school lab setting. But 2,4-dinitrophenylhydrazine, this sort of orange sort of coloured solid, can be used to identify aldehydes and ketones, or can be used to detect the presence of the aldehyde and ketone functional groups. So let's look at the molecule itself. Let's look at the reagent. So where does the name's always a good place to start from. What does 2,4-dinitrophenylhydrazine look like? Well, we can start by looking at the hydrazine part of the name. So if we highlight that bit there, the hydrazine part refers to this bit here. Okay, so hydrazine itself is a molecule that is related to ammonia. If you swapped one of the hydrogens of ammonia with an NH2 group, what you've got is hydrazine. Okay, so 2,4-dinitrophenylhydrazine. The phenyl group, of course, refers to the benzene ring. If we pick a different highlighter for it, so here's your phenyl group. Okay, and the dinitro, of course, refers to the two NO2 groups that have a 2,4 relationship to the hydrazine group. So one nitro group is at position number 2, and the other is at position number 4. And these nitro groups, again, if we pick a different highlighter for them, so you've got that and that. So you've got 2,4-dinitrophenylhydrazine. Now, the hydrazine part of your 2,4-DNP molecule acts as a nucleophile, and indeed it's the NH2 group at the end, and the lone pair on the nitrogen of that NH2 group acts as a nucleophile and attacks your carbonyl group, the carbon of the carbonyl group. And it's quite a lengthy mechanism. In effect, it can be described as an addition-elimination mechanism, something that not all boards require you to know. But the upshot of that reaction between the hydrazine, NH2, and the carbonyl is that you end up forming a hydrazone derivative. So let's highlight that. So this here is your 2,4-dinitrophenylhydrazone derivative. So the hydrazone part comes from, let's stick to yellow. So that yellow bit there is the hydrazone group. Okay, and these are sort of orange solids. So especially if they are a hydrazone with a phenyl group as part of the structure. So you'll get an orange precipitate formed, and that will be an indication that you've got you had a carbonyl group present to start with, or the carbonyl of an aldehyde or a ketone. So if the aldehyde or ketone does not have an aromatic group, then the yellow, the precipitate formed is more yellow in color. That's a little bit of detail that we don't look at A level. Okay, so you've got a hydrazone derivative formed if you've got a carbonyl group from a ketone or an aldehyde. And the color of this hydrazone derivative is orange, and of course the derivative itself is a solid. Okay, so the test itself allows you to identify the presence of an aldehyde or ketone group in a compound, but it doesn't distinguish between the two. Okay? So that's something that is important for you to pick out. So it will tell you that there is a carbonyl present, but that carbonyl group could be for a ketone or for an aldehyde. What it won't do is identify that you've got a ketone or an aldehyde. However, you can take this test one step further. If after making your hydrazone precipitate, the orange solid, you then purify it and then dry it and take a melting point of it, you can compare that melting point to data book values that would allow you to identify the specific aldehyde or ketone that makes the hydrazone derivative of that melting point. Okay, so just taking the melting point of the precipitate and comparing it to data book values allows identification of the actual aldehyde or ketone. So it's something to remember because it can be sort of tested. Okay, so at present, there are no questions on the first two functional groups, so we will continue looking at the subsequent groups that we're interested in. Now, we've got a test that identifies the carbonyl C double bond O group in an aldehyde or ketone, but can we actually have a test that positively identifies an aldehyde and therefore can be used to distinguish between aldehydes and ketones? The answer, of course, is yes, and there are at least two that you will see at A level. So let's have a look at those. Okay, so this screen is split into two parts, looking at the two tests that you could use to positively identify an aldehyde. And both of these tests involve the use of reagents that are mild oxidizing agents. So the tests rely on the ability to oxidize an aldehyde further to a carboxylic acid, whereas the ketone carbonyl can't be oxidized any further. Okay, so the first reagent we're going to look at is Tollens reagent. A Tollens reagent is also known as ammoniacal silver nitrate. Okay, and that's to do with how the reagent itself is formed. As I said, it is a mild oxidizing agent, and as a link to your work on transition metal chemistry, this Tollens reagent has the active silver 1 complex ion shown, the diamino silver 1 complex ion here, as the active ingredient. Okay, so that is your active oxidizing agent in your Tollens reagent. Okay, so how do we make this diamino silver 1 complex? It's fairly straightforward. You take a centimeter cube of silver nitrate into a clean test tube. It's important to emphasize that the test tube has to be clean, otherwise the observation made at the end isn't as isn't as pretty, for want of a better word, and you'll see what I mean in a second. So we're looking at adding 1 centimeter cube of our silver nitrate to a clean test tube, and then we're going to add some sodium hydroxide. Okay, so having done so, you should form a precipitate of silver oxide. Now, that precipitate formed will dissolve when you add enough ammonia to form the diamino complex. Okay, so we form silver oxide, which we then dissolve by adding ammonia dropwise to the precipitate. Okay, so once that precipitate has disappeared, once it's been dissolved, you've got your reagent. You're ready to use this reagent in a test. Now, how do we carry out the test? So you've got an unknown liquid, which could be an aldehyde or it could be a ketone. You're going to take a few drops of the aldehyde or ketone. You're going to add your drops to your Tollens reagent that you've just prepared. And then it is important that you gently warm your mixture or heat the mixture in order to get a positive test. How do you do that? You're going to leave your test tube containing the reagent and the unknown mixture in a water bath, in a warm or hot water bath. Okay, so we're going to add a few drops of the unknown to our Tollens reagent, and it's important that you warm that. That experimental detail is critical for getting full marks in a description. Okay, so we're going to warm it, and if there is an aldehyde present, it should be oxidized to carboxylic acid. Now, if it is being oxidized to carboxylic acid, something must be being reduced, right? We've got silver 1, the silver 1 complex, and the silver ion is going to be reduced to silver atoms. The element silver is going to be formed. And you'll see this as a shiny silver coating on the inside of your glassware. And here's why it's critical to have a very clean test tube, because without a very clean test tube, you don't get the very beautiful sort of silver coating. What you get is amorphous silver. You get a grey sludge in your test tube, which is also evidence of the presence of an aldehyde, but it's not as pretty as having a nice silver coating on the inside of your test tube. So make sure you're using a very clean test tube when you carry out the test for an aldehyde, using Tollens reagent. Okay, so let's look at the equation down at the bottom of that page there. So you've got your aldehyde there, and it is, of course, being oxidized to the carboxylic acid. And we can show exactly that. So this here is your oxidation. And if we use a different color, if we pick, I guess we can pick this purple color, you've got your silver ions becoming the element silver. And of course, that is a reduction. Remember, the reduction is the gain of electrons, so Ag plus gains an electron to become Ag. And so here is our reduction. Okay, and if I can zoom in on the test tube down at the bottom underneath our Ag or silver, you can see it's a very shiny silver coating on the inside of the test tube when you've got a positive result for the presence of an aldehyde. Okay, so the other reagent you could use if you don't have Tollens available is Phenolic reagent. Now, Phenolic uses a different transition metal metal ion as the oxidizing agent. In this case, it is copper 2+, and the active complex is so copper 2+ with tartaric acid as a ligand. So if you're again sort of linking this back to your inorganic chemistry and transition metal chemistry, you've got tartarate or derived from tartaric acid as the ligand in your Phenolic solution. Now, it is an oxidizing agent working on the same principle as Tollens, and it comes to make your Phenolic reagent. You need to start with hexaaqua copper 2, so copper sulfate solution to use simpler terms. And so we've got 1 centimeters cubed of Phenolic A, which contains which is essentially copper sulfate solution, and to that you're going to add an alkaline solution of Phenolic B. Phenolic B contains your tartaric acid dissolved in an alkaline solution, so sodium hydroxide solution could be an example. And when you mix Phenolic A and Phenolic B together, so Phenolic B is colorless, Phenolic A is a blue color, as you would expect with copper sulfate solution. Mixing the two gives you a very deep, intense blue color, which is your Phenolic reagent. So you would have made your copper complex to tartarate to give you that active ingredient. Okay. So you've got a deep blue solution now. What do you do as far as the test goes? You're going to add a few drops of your unknown compound to this deep blue solution, and then you're going to warm it just as you did for Tollens. So you're going to add a few drops of the unknown to Phenolic solution and warm gently. And this time round, if there is an aldehyde present, you're going to get a brick red precipitate. Now, this brick red precipitate is actually a compound of copper 1. So it is actually copper oxide. So copper 1 oxide formed. Okay, so looking at the equation again, you've got your aldehyde going to the carboxylic acid. That's, of course, oxidation. And you've got your copper 2+ being reduced to copper 1 in your Cu2O. So we go from 2+ there, that is, of course, a reduction. And we can zoom into the two test tubes for before and after. And if we can look at that on our screens, you've got your Phenolic reagent. So if we highlight that, so let's take a different highlighter. So there we go. So there's your Phenolic reagent highlighted there. And then this is the evidence of the presence of copper 2 oxide, so that brick red precipitate, which of course can only be formed if you had an aldehyde in the first place that was oxidized. Okay, so that is Phenolic reagent, which could be an alternative to Tollens reagent. Okay, so at this stage, there are no questions, so we will press on. And if we next look at alcohols and being able to identify the different types of alcohols present. Now, primary and secondary alcohols can be identified using an oxidizing agent. We know that because we can oxidize the primary alcohol to an aldehyde and then even further to a carboxylic acid. And we can oxidize a secondary alcohol to a ketone. So if we've got a primary or secondary alcohol present, we should be able to detect it by looking at the change in color of the oxidizing agent that we use. Okay, so oxidation, especially with reagents that contain transition metal ions, will show or undergo a color change to indicate the change in oxidation state. Okay, so if we choose to use acidified dichromate, which is our oxidizing agent of choice, your dichromate contains chromium ions in the +6 oxidation state. And of course, when these chromium ions themselves are reduced, they go to the +3 oxidation state, so we form chromium 3+. And the chromium 3+, of course, is a green color, different to the orange color of your chromium 6 in dichromate. Okay, so let's look at this way of distinguishing primary and secondary alcohols from tertiary alcohols, which do not react at all and can't be oxidized. Okay, so in this test, you're going to add acidified potassium dichromate, about 3 centimeters cubed of it, to a boiling tube. And to that acidified dichromate solution, you're going to add about 1 centimeter cubed of the unknown. So my spelling has gone a bit awry there. Let's put an N at the end of unknown. Okay, so you're going to be adding your unknown to your acidified potassium dichromate, and then you're going to be heating gently, and the orange solution should turn green. Okay, so the orange solution, if we pick a different highlighter, so this orange solution is the dichromate. Okay, and the green color is, so this is chromium 6, Cr in the +6 oxidation state. And the green solution is your contains your chromium 3 oxidation state. Okay, so that's what's happening to our oxidizing agent. It's changing color from orange to green because we've got a primary or secondary alcohol present. Let's look at the example where a primary alcohol is oxidized to the aldehyde. Of course, it could be oxidized to carboxylic acid as well, but I've just chosen the aldehyde for no particular reason. So let's look at the redox half equation. So remember, this is redox chemistry, and you can link it back to your work on redox reactions and writing redox half equations and overall equations. So you've got a primary alcohol, which is being oxidized. So let's highlight these. So you've got your primary alcohol here, and it is being oxidized to an aldehyde there. Okay, so the half equation, if we look at the half equation to make sure that it is balanced, you've got so you've got the right numbers of hydrogens on both sides. So if you count all of the hydrogens here, you've got 1, 2, 3, 4, 5, 6, 7, 8. You've got 8 hydrogens in your propanol, and you should have 8 hydrogens altogether on the right-hand side. So you've got 1, 2, 3, 4, 5, 6, 7, 8. So you've got 8 hydrogens on the right, and the charges on both sides are the same. There's 0 charge on the left, and there's 0 charge on the right. So you've got 2 pluses and 2 minuses, which cancel out. So everything looks balanced. All the atoms of the different elements, you've got the same number on both sides. And then if we look at the oxidizing agent, which is our dichromate, you've got your chromium 6, so +6 oxidation state for chromium, and it is going to +3. There we go, and it is gaining electrons in order to do that. So each mole of your, to work out how many, so each mole of our dichromate will require 6 moles of electrons. So there are 2 chromium species in your dichromate, so each of those picks up 3 moles of electrons to give you your 2 moles of Cr3 plus. Okay, and of course, in order to supply the 6 moles of electrons that you need, you're going to need to have more than 1 mole of your alcohol to supply those electrons. In fact, you're going to need 3 moles of your alcohol to do that. So we need 3 times there to produce the right number of electrons. And of course, you can then sum up the 2 half equations to get the overall equation. Okay, so that's a little bit more sort of insight into what's going on in this actual chemical test. We're oxidizing our alcohol to an aldehyde, but the oxidizing agent itself, of course, has to be reduced. The oxidizing agent is your dichromate, and that is being reduced to chromium 3+. So you've got dichromate containing +6 chromium oxidation state, and the chromium 3+, which is, of course, +3. And the colors, to re-emphasize this point, you've got orange dichromate, and you've got green chromium 3+. Okay, so that's your test for alcohols, so primary and secondary alcohol. Of course, a tertiary alcohol cannot be oxidized. So if we drew an example of a tertiary alcohol, so that could be this one here, so methyl propan-2-ol cannot be oxidized. So no reaction. There's no reaction with tertiary alcohols, and that's because the carbon to which the OH group is attached does not have any hydrogens bonded to it. So typically, we're talking about to primary and secondary alcohols being able to be oxidized. Good. So that's alcohols. We've got another couple of functional groups. In fact, we've got 3 more functional groups to look at, and then we'll end the session by looking at some practice exam questions. The first one to take on first is carboxylic acids. And for carboxylic acids, you want to react them with a metal carbonate, usually a group 1 sort of carbonate. You can often form solutions with group 1 metal carbonates, but you can also use a solid carbonate. So if we take a spatula of sodium carbonate and add it to a centimeter cubed of our unknown solution, so a spatula of solid sodium carbonate, and again, I seem to be missing out the end of my. There we go. So a spatula of solid sodium carbonate, and if there is a carboxylic acid present, there should be fizzing as a result of carbon dioxide being formed. Okay, so you're going to get fizzing occur if a carboxylic acid is present, and if we look at the balance equation, CO2 being formed is why you get fizzing. So that bubbling CO2 gas through your solution indicates that you do have a carboxylic acid group. Okay, so that's carboxylic acids. Now, phenolic OH groups or phenols are also acidic. They are weakly acidic, in fact, very weakly acidic, and so much weaker than carboxylic acid groups. So it's important to note that point there. And because they're much more weakly acidic, they do not react with your metal carbonate. So will not react with sodium carbonate. Okay, so you can you can react if you had 2 unknowns and you were told one of these was a carboxylic acid and the other was phenol. What you would do is use sodium carbonate to discriminate between the 2. So the carboxylic acid would react with sodium carbonate. The phenol will not react with sodium carbonate. Phenols will, because they are acidic, will react with metals, so sodium on its own, in much the same way that acids will react with metal to give you the sodium salt and hydrogen gas. So that's this equation shown here. So phenols will react with reactive metals, and they'll also react with a strong alkali such as sodium hydroxide, okay, but not with sodium carbonate. And the final functional group that we want to look at is the halogenoalkanes. So these are, so in effect, we're talking about the carbon-halogen bond and how to detect the presence of such halogens in an organic molecule. So you've got the three halogens we're most interested in at A level are chlorine, bromine, and iodine, and it is to a lesser extent fluorine as well, but this is more when we come to talk about the different rates of reaction or hydrolysis of the carbon halogen bond. How do we identify the presence of the carbon halogen bond in the first place? Well, you want to hydrolyze the carbon halogen bond first, which of course would produce a halide ion. Now that halide ion can be detected if it forms a precipitate with another species. So in this case, we use silver ions from silver nitrate, and the silver halide formed precipitates out of solution. It's a solid, it will crash out of solution, and depending on the color of the precipitate formed, we can then decide if it's a chloride or a bromide or an iodide. Okay, so as far as the test goes, you're going to add some silver nitrate solution to a test tube, and you're going to add 3 drops of your unknown to that test tube. And if there is any carbon halogen bonds formed, then you would first have a hydrolysis of that carbon halogen bond and an immediate or almost immediate formation of a silver halide precipitate. Okay, so we're forming a silver halide precipitate, and these vary in color. So silver chloride would be a white precipitate, and silver bromide would be cream, and silver iodide would be yellow. And the rate at which the different silver halides form can also be used to indicate whether they are chlorides, bromides, or iodides. Of course, you would need to do this quantitatively and to compare the 3 unknown halides at the same time. So if you've got your silver nitrate solution and you add your sort of equal volumes or amounts of each of the unknowns at the same time and press start on your clock, the first precipitate to form would be the sorry, I think I do have an error on my slide here. So that should be. I've just noticed that there we go. So that should have been decreasing rate of formation of our precipitate. Okay, so the first precipitate you ought to see is the silver iodide precipitate, and that's because the carbon iodine bond is the weakest of the 3. The carbon iodine bond has the lowest bond energy. And so it's more readily broken. So your your carbon chlorine bond, on the other hand, is much stronger, has a much higher bond enthalpy, so not a lot more energy required to break it, so not as readily broken. Okay, so the arrow is showing decreasing rate of formation of precipitate. So you're going to get your silver iodide formed much more quickly than silver chloride. Okay, silver iodide is yellow, silver chloride is white. Of course, silver bromide in the middle is green and is of an intermediate sort of rate of hydrolysis, somewhere between the very slow carbon chlorine bond being broken and the much faster carbon iodine bond, I should say. Okay, so you're going to add your drops of unknown to silver nitrate, and you're going to look out for the formation of a precipitate. Okay, and the equations are shown here. And so what's going on? The first part is, we highlight this, that part of the reaction is your hydrolysis. And then the second part is formation of a precipitate. Okay, so there are 2 parts to the the tests for halogenoalkanes. Okay, so at this point, it would be a good idea to see if there are any questions. Just checking my chat box. No questions in a minute, so we will continue. And the next thing to do is to put everything we've looked at, bring everything we've looked at to answer some practice questions. I've picked a couple of exam questions from the A-level papers from 2017 and 2018, and we're looking at paper 2, both of which test your knowledge and understanding of ability to apply test tube reactions to identify organic functional groups. This question's from the 2017 paper, and we're looking at question 20, part B of 2017, and we're told that qualitative tests are carried out on the aromatic compound. So we've got an aromatic compound here, it's an important detail. The results are shown below. So the acidity of this aromatic compound is pH 5, so it is acidic, but weakly acidic. It doesn't react with sodium carbonate, so there's no formation of carbon dioxide. So we know it's not a carboxylic acid. So it's perhaps useful to make that point. So not a carboxylic acid. So it's not a carboxylic acid, but it is acidic, and that's interesting. We only know of one sort of functional group, so we could begin to think possibly phenol. We also know that it is an aromatic compound, so looking likely. We're told that a reaction with 2,4-DNP produces an orange precipitate. Okay, so this orange precipitate here is suggestive of a carbonyl of a ketone or aldehyde. So C double bond O for ketone or aldehyde. But because we know that there are no observations with Tollens reagent, we can assume that it's, well, not assume, we can correctly conclude that it is a presence of a ketone carbonyl that's giving the orange precipitate. There's no silver mirror fault. Now you say, the question says we are to determine the functional groups in the compound and explain our reasoning. Okay, so the functional groups are phenol OH, so phenolic OH. We know we've got a ketone present as well. Okay, any other conclusions? So we know it's a phenol because it's acidic, but it doesn't react with sodium carbonate. We know it's a carbonyl of a ketone because we get an orange precipitate, which doesn't give us a silver mirror. Okay, so let's write that down. So phenol because weakly acidic, but no reaction with sodium carbonate, and we know it's an aldehyde, sorry, rather ketone because 2,4-DNP gives orange precipitate. But no silver mirror. With Tollens. Okay, so that's our that's the sort of question that you would be required to answer as far as qualitative tests or functional groups go. So it's not just a case of being able to recall and sort of recite sort of the test carried out and the observations made, but you've got to be able to use the idea, sort of not the idea, but rather your knowledge to, and you've got to be able to apply it to a scenario that sort of requires you to identify sort of particular groups in a mystery compound. So let's take a look at another question that again looks at qualitative analysis of organic groups. So if we zoom in a bit more, there we go. So in this question, the student plans to carry out some chemical tests on both cinnamaldehyde and methyl cinnamaldehyde. So cinnamaldehyde is on the left, methylcinnamaldehyde is on the right. So just a suitable chemical test to confirm that both compounds contain an unsaturated chain. So this is the typical test for unsaturation. So we pick up our highlighter, so suitable chemical test, okay, to confirm that both compounds are unsaturated. So in other words, how would you identify these carbon-carbon double bonds as being present? Okay, so your answer should include the reagent and observation. So you need to be saying at least two things for just the one mark. Okay, so our reagent, of course, is going to be bromine water. And bromine water is decolorized. Of course, decolorized means going from orange to colorless. Okay, so that's one mark, but a bit of information required to get that one mark. Now, in part two, we're asked to describe a chemical test to confirm that both compounds contain an aldehyde functional group. So again, if we look at our cinnamaldehyde, it's got an aldehyde group there. Methylcinnamaldehyde's got an aldehyde group there. And so we want to suggest a reagent and what observations you would see. The reagent, of course, would be Tollens reagent. And we're going to see a silver mirror on warming. Okay, so that is sort of pretty straightforward. And then in part three, we're asked to describe a chemical test to confirm that cinnamaldehyde and methylcinnamaldehyde contain a carbonyl group. So how could the products of this test be used to distinguish between the two compounds? Your answer should not include spectroscopy. So quite a bit more involved in this question. So we've got there's a chemical test to confirm that cinnamaldehyde contains a carbonyl group. It says how could, so three parts of this, how could the products of this test be used to distinguish? So using the products to distinguish between the two compounds, and answer must not include spectroscopy. Okay, so these are things to bear in mind when answering the question. So of course the reagent we want to use is 2,4-DNP. So 2,4-DNP, which would produce an orange precipitate of hydrazone. Now, how could the products of this test, so hydrazone for each of cinnamaldehyde and methylcinnamaldehyde. Okay, so we've made the orange precipitate, the hydrazone derivative for each of our aldehydes. How can we use these orange precipitates to distinguish between the two compounds? We can find melting points. Find melting point of each dried precipitate and compare to database values to identify the aldehyde. Okay, so that's quite a bit of information to get 3 marks. You need to state the reagent, so using 2,4-dinitrophenylhydrazine, 2,4-DNP, which produces an orange precipitate if there is a carbonyl group present, so that's 1 mark. You would then need to dry your orange precipitate and take its melting point, and when you've done that, compare the value of the melting point to what's in the data book or in a database to identify the specific aldehyde. And no spectroscopy is used at all in this process. Okay, so that's been quite a quick sort of whirlwind tour of qualitative analysis. I hope that you have found it useful, and certainly will find it useful when you re-watch this live. As usual, if there are any questions at all on what we've discussed on chemical analysis and specific chemical tests, do drop us a line and we will be more than happy to write back to you. Do use the comments or email us, comment box, or use or email us at boostrevision.com and we will write straight back with an answer for you. Thank you very much for joining me. It's been a pleasure. I look forward to seeing you again. Thank you.